This section is on applications of the integral to physics and engineering. And the two applications I'll be focusing on are fluid forces and centers of mass. So I'm going to do this video in two parts. The first one will be on fluid forces, and then the second part will focus on centers of mass. It says here, when engineers design dams, they make them thicker at the bottom than at the top because the pressure against the dam increases as the distance below the surface increases. So it needs to be able to withstand greater fluid forces. Suppose we need to find the force exerted on a wall that is submerged below the water surface. So first we just revisit Newton's second law, which says force is equal to mass times acceleration. Here I have it in vector form. We'll be dealing with it in scalar form. But in your physics classes, or if you take Calc 3, you may look at the vector form of the equation. In these problems, acceleration will always be the acceleration due to gravity. In the, that should say, metric system, the acceleration due to gravity is about 9.8 meters per second squared. In the English system, we'll be using 32 feet per second squared. In some books, you may see 32.2. We'll be using 32. In the metric system, we will be told the density of the liquid as a mass per unit volume. So in the metric system, it will be either like kilograms per cubic meter or kilograms per liter. In the English system, we'll be given the density as weight per unit volume, so pounds per cubic foot. If you've taken physics, you know that weight is equal to mass times gravity, which is like mass times acceleration. So weight is a force. So we'll be given enough information to find the volume. We will also need to have enough information to find the volume of the tank or container or body of water. So in the metric system, rho times V is equal to, this M stands for mass. And think of that, what I have up here. So if these are our units and we multiply by a volume, which would be either cubic meters or liters, they cancel and we're just left with kilograms, which is a unit of mass. Updating the force equation in the metric system, then all I'm doing is plugging this expression in for mass. So force equals, this is our mass times, and then the acceleration due to gravity. So there's the formula for the force in the metric system. Force equals, this is called a rho, Vg. We'll almost always be given the value of rho, and we know the value of G, so we have to find volume ourselves. To find the volume of water, we'll think of the volume of water as pressing on the plate. What we'll do is we'll find the area of the plate and then multiply by the depth of the water above the plate. So first I'm going to think of just if I have a small plate here and then there's a bunch of water above it pressing down on it, right? So we'll have kind of this rectangular slab. So we'll have the area of the plate at the bottom times the depth of the water. So we'll have like a length times width times depth. So all I did here was replaced volume with area times depth, where area is the area of that plate. That's the metric system. Now the English system. In the English system, rho times V equals the weight. And I have to look at this over here for the English system. So rho is pounds per cubic feet and volume will be in cubic feet. So the cubic feet will cancel and we'll be left with pounds, which is the unit for weight. And then I just went to the force equals mass times acceleration equation. But remember, weight is a force. So I have rho V equals ma, but the acceleration is the acceleration due to gravity. And then you can solve for mass to get that. Just divide both sides by the acceleration due to gravity. And then plugging this in for mass, we'd see the A is the acceleration due to gravity, so they would cancel and we would just be left with rho times V. And as before, the volume is going to be replaced by the area of the plate times the depth of water pressing down on that plate. Okay, so two slightly different formulas for the metric system and the English system. The only difference is for the metric system, we have to multiply by the acceleration due to gravity. We don't do that in the English system. Fluid force on a constant depth surface. So it says those equations work well for finding the force exerted on the base of a rectangular tank, since every part of the base is at the same depth. So if I had here, I just drew a little strip, but suppose you put a bunch of those little strips together to make a rectangular tank. Every single strip has the same depth of water acting on it. But it says we could also have a plate, quote unquote, submerged vertically, like the side walls of an aquarium. So like this part, you could also do the front wall or the back wall. But if you split that one up into strips, every strip is at a different depth. So every little strip is going to have a different force acting on it. And then it says right here, by dividing the plate into many horizontal bands or strips, like I just did, we can create a Riemann sum whose limit is the fluid force against the side of the submerged vertical plate. So let's look at setting up that integral. I am always going to set up my integrals with respect to y. It just makes more sense to me to think of up and down as y, but I think the book does x. Their solutions would be the exact same as mine. They just have y in place of x. I don't care which letter you use. You can follow the book's convention or mine. So the integral for fluid force against a vertical flat plate. Suppose that a plate submerged vertically in a fluid of mass density rho runs from y equals a to y equals b on the y-axis. So this right here would be y equals a, and this right here would be y equals b. Let L of y be the length of the horizontal strip. So remember, for the vertical plates, we separate them into lots of different horizontal strips. Those should be straight lines. So if I look at just one particular strip, an important thing to note here is that my strips all have different widths or lengths, right? Depending on what depth I am at, right? So the shortest ones are at the bottom and the top, and the longest ones are in the middle. So the length might be a function of the depth or a function of y. The force exerted on that strip is given by, this is right here, assuming we're in the metric system because I'm multiplying by g at the end. So remember, for metric, the force is equal to, well, if we look back here, for metric, it was rho a d g. For the English system, it was just rho a d, where rho is the density, a is the area of the strip, and d is the depth of the strip. The strip area, I'm always going to think of it, if I make them small enough, the horizontal strip looks rectangular. I know this has sides that are at a slant here, but if you make them small enough, it looks a lot like a rectangle. And if you remember back to Calc 1, we always used rectangles to approximate as well. So what I want to do for each strip is think of, okay, if that were a rectangle, I would do like base times height. And the base is what they're going to be calling the length of the strip. And the height, I would just call that my delta y, right? Think of when you were doing Riemann sums in Calc 1, the bases of your rectangles were called delta x. So the height is always going to be delta y. The length is changing depending on where you are in the strip. So I have that here. The strip area is replaced by length times height, and then the strip depth, and then times g. As we'll see when we start to do problems, you're free to put the origin wherever you want. Most of our plates are going to be symmetrical, so I would put the y-axis going through the center. Then you can choose to put the x-axis wherever you want. And there are kind of 4 convenient choices. You could put it at the bottom and call the bottom y equals 0. That is nice. You could put the bottom right here at the bottom of the plate. There's another advantage to putting it there. You could put it at the top of the plate if you want, or you could put it at the surface of the liquid. The 2 at the top, for me, don't make as much sense, at least in this picture. So I would either choose y equals 0 to be right here or y equals 0 to be right here. I kind of like to have 0 at the bottom so I don't have to deal with any negatives. So I would probably call that y equals 0. I'm going to call then the top just y equals capital S for like surface level. So that's however deep the container is or body of water or whatever. When I do that, my strip depth is always going to be surface level minus y. Sometimes the book will call positive down in these problems. Then you can't use this idea. I always make positive up, and then I can always use strip depth equals surface minus y. The strip depth is how much fluid is above the strip or pressing down on that strip. So just say, for example, that this was 10 meters or 10 feet, whichever. I'm assuming metric system here since we're multiplying by g. So say it was a total of 10 meters deep. So say we just picked a random strip here, and if it was 6 feet above the bottom, how much water is pressing down on it? Well, if this part is 6 feet, then what's above it is 4 feet, right? 10 minus 6. So it's always going to be surface minus y. What if I decided to call the bottom of the plate 0? Well, then this isn't going to be 10 anymore. Let's just say this was 2 meters. Then the bottom would be y equals negative 2, and the top would be 8 meters, right? Then we still have a depth of 10 meters. And if something was 6 feet above the bottom, what would the y coordinate be? Well, it would be y equals 4, right? And if I look at that strip depth, it's still surface level minus y, right? So you can use different coordinate systems. It's just going to affect, as we'll see, your limits of integration. Sometimes one arrangement will be more convenient than another, and we'll see that in a later example. So this was the force pressing on one strip. So to get the total force exerted on the entire vertical plate, we just add up the forces from each strip. So here the total force is the sum of the forces exerted on individual strips. Each individual strip, the expression is rho. All I did here was pull the g, it's a constant, out in front. I always move the delta y or delta x to the end because that's going to turn into dx or dy. So what's left then is the length as a function of y and the strip depth. And then when you take the limit as n goes to infinity, the summation turns into the integral sign and the delta y turns into dy. Okay, how to find fluid force. We'll follow these steps as we go through an example. This one, look at, we're in the English system. So that means the force is just rho AD. And A stands for area, which is length times width. And then we'll have times D is depth. Since my strip width, I have my picture here, is a delta y, that means we're going to be integrating with respect to y. Again, this is my personal preference. The book might do x. I will always give this to you, the density. So the weight density of water is 62.5 pounds per cubic foot. This is fresh water. When you look at salt water, it changes a little bit. Okay, so the strip depth is always the way I set it up when I have the y-axis going through the center and positive is up. The strip depth is always surface minus y. And I've imposed a coordinate system here for us where the surface level is 5. So it would be 5 minus y. The strip length. Now you can see as you move through that plate, your strips are changing length. So it's not going to be just a number. It's going to be a function of y. So first of all, I've labeled a point on the right edge of the strip as just xy. Now you might look at this picture and say, okay, well, the length of that strip is a horizontal distance, so it's going to be related to the x value, which is true. But if I'm integrating with respect to y, I have to get everything in terms of y. So first of all, the strip length will be 2 times the x coordinate, but I have to change that. And they have told us right here that the edge of the plate lies along the line y equals x. So I can replace the x with y or just substitute in. So if I substitute y in for x, I get 2y. So what do we have? So we're given the row. I just found an expression for length. The width is delta y, and the depth is 5 minus y. So we have everything we need to set up our integral. So the force, I'll talk about the limits on the integral in just a minute. So the rho is 62.5. I'm going to leave units off until the very end. Length is 2y. Width is delta y, which turns into dy at the end. And then the depth is 5 minus y. Okay, the limits, a lot of people get confused about the limits because you see, well, the water is going from 0 to 5. We don't care so much where the water is going. We care where our strips are going. Where do our strips go from? Well, our strips start at the bottom of the triangle, which is y equals 0, and they go to the top of the triangle, which is y equals 3. So our limits on the integral are 0 to 3. So I am going to pull the 62.5 out in front of the integral. If you want to pull out the 2 as well, I think I'll just leave the 2. Can do that. And then distribute either the y. If you also brought out the 2, I'm going to distribute the 2y. So I would get 10y minus 2y squared. Okay, that's a polynomial. We can go ahead and integrate that. So the antiderivative of 10y would be 5y squared minus 2, and then it would be 1/3 y cubed. So 2/3 y cubed, and this is going from 0 to 3. So if I plug in 3, 5 times 9 is 45, minus 2/3, and then 3 cubed is 27, minus what I get when I plug in 0, but both times I would get 0. And then 3 goes into 27 9 times. So I would get 62.5 times 45 minus 2 times 9 is 18. And 45 minus 18 is 27. And then you can do that on your calculator. And I get 1687.5. And then for your final answer, I want to see units. This is a force. We're in the English system, so it's pounds. If we were in the metric system, it would be newtons. So just a note. So metric force is in newtons. And a newton is 1 kilogram times meter per second squared. Because this right here, that's your mass, and this is your acceleration. Okay, next problem. Suppose a plate is placed so that part of the plate sticks out above the surface of a lake, as shown here. What force does the water exert on one face of the plate? The reason they say one face is because there's water pressing on the side that's like in front of the paper, and then water like behind the paper, right? We're in 3 dimensions. We're just going to find the force on the side facing us. Again, I see units that indicate we're in the English system. So force is equal to rho AD, where A is the area of a strip. So I'm going to do length, which is again a function of y, because as you move up through the triangle, they get shorter. The width is always going to be our delta y, and then our depth. In order to figure out depth, I have to decide where to put my origin. Well, I'm going to have the y-axis go right through the middle. Then you can either choose to have y equals 0 at the bottom of the plate, or y equals 0 at the surface level. I'll show you that we would get the same thing either way. I will start out doing this as y equals 0. In fact, I think I'm going to change it almost immediately. So let's start identifying stuff. So we're in a lake, assuming that's fresh water. So rho equals 62.5 pounds per cubic foot. And then the length. Okay, I'm going to hold off on that. The width, delta y. And then the depth will be surface minus y. But the surface level depends on where I put the origin. If I leave it the way I have it drawn right now, what would the surface level be? It's not the top of the triangle, right? Here's the surface level. So it would be 1. I'm going to explain why I'm going to change my coordinate system. Because I have to get the equation of length as a function of y. So if I label this point on the edge as my xy, in terms of x, right, this is half of the strip, so I would just multiply that by 2. So it'd be 2x, but if everything else is in terms of y, I need my length in terms of y. The right edge of my strip goes out to this line. So I would have to write the equation of that line in y equals mx plus b form, and then solve for x in terms of y. It's not like it's hard. The slope is we go down 4 and over 2. So the slope would be -2. My y-intercept would be 4 because we've gone up 1 and then 3. But it's really nice actually if I put the origin up here, because then my y-intercept is 0. And then the equation of this line, y equals mx plus b, well, now I go down 4 and still over 2. So it'd be -2x, but then plus 0. So my x is y over -2 or -1/2 y. So I get 2 times -1/2 y, which is -y. Then the depth of a strip, the surface level, what is the surface level? This is 0, so the surface level is we've gone down 3 units. So this would be y equals -3. And this right here would be y equals -4. So my surface level is -3, so I would have -3 minus y. And then I have everything I need to set up the integral except for the limits, but we'll figure that out after we set stuff up. Okay, so rho is 62.5. Length is -y. The delta y I'm putting at the end, it turns into dy when we take the limit, and the depth is -3 minus y. Okay, now the limits on my integral, and the limits refer to the strips. Where do my strips start and stop? The first strip at the bottom will be at y equals -4. Where's the last strip? At -3, because then the rest of the plate is out of the water and there would be no fluid forces. So my limits are -4 to -3. So I am going to pull the 62.5 out in front, and I'm going to distribute that -y through. So negative times negative is positive. Negative times negative is positive. And then we can integrate. So it'd be 3/2 y squared plus 1/3 y cubed. This is going from -4 to -3. Okay, so I have 3/2 times 9 plus 1/3 times -27 minus what I get when I plug in -4. So that would be 3/2 times 16 plus 1/3 times -64. Okay, so this is 27 over 2. 3 goes into 27 9 times, so minus 9. 2 goes into 16 8 times, so minus 24. And then minus negative, so plus 64 over 3. This is -33. I'm just going to do this on my calculator, and I get 1375 over 12, or a decimal approximation would be 114.6. And then the units on this, on each of these, would be pounds. I'm just going to show you quickly that if I had put the y equals 0 at the bottom, we'd still get the same answer. Our setup would be different, but we would get the same answer. So if I put y equals 0 at the bottom, then the surface level of the water is 1 foot up, so that would be y equals 1. So my limits would be 0 to 1. The rho is still 62.5. But then you may remember me saying that the equation of this line, if I put the y equals 0 at the bottom, the y-intercept was 4 and the slope was -2. So -2x plus 4. And then we would have to solve for x in terms of y. So I'd get y minus 4 equals -2, and then -2x, and then divide both sides by -2. So I'd get x equals -1/2 y plus 2. And then to get the length, we have to multiply the x by 2. So I would get -y plus 4. What would be the depth of a strip? The depth, the way I set it up, is always surface minus y, but our surface level is 1. So it would be 1 minus y, and then dy. So here you'd have to do FOIL, multiply out, and integrate. I'm going to pause the video, do that, and then come back. And you can see that we get the same answer either way. Okay, so I just finished the problem with the different setup, and I got the same thing. If you want to copy down the work, pause the video and look at it, but it worked out to the same value for force. Okay, there's, I think, one more problem before we get to centers of mass. So here it says the rectangular tank shown here has a 1 foot by 1 foot square window 1 foot above the base. So I'm just going to label this drawing here. Okay, and then it says the window is designed to withstand a fluid force of 312 pounds without cracking. And notice they're just talking about the window, that little 1 by 1 square. What fluid force will the window have to withstand if the tank is filled with water to a depth of 3 feet? So again, we have a choice of where to put the origin. I think it might just be easier to put it at the bottom of the tank. So I'm going to put y equals 0 here at the bottom, which means the bottom part of the window would be at y equals 1, and the top part of the window would be at y equals 2. And then in part A, they're saying the water will be in there to a depth of 3 feet. So I may have already mentioned this, but since they're saying feet, we know we're in the English system. So force equals rho AD. And then remember, just because we haven't done one with the metric system for a while, if this was meters, we would do force equals AD, and then we'd have our G here at the end. Okay, so again, they're saying water. So And they don't specify that it's salt water, so we'll just assume regular water. And the rho is 62.5 cubic feet. This is not something you'd need to memorize. I would give you this information. The area, remember, when they say area, what they mean is area of a strip. We're going to break that window into little strips, right? So what would be the area of that strip? It would be the length, which in this case, the window is the same all the way through. The length of a strip is going to be 1 foot. And the width, or you can talk about it as base and height, the height would be delta y. So the area is length times width. And as I just mentioned, the length is going to be 1 foot, and the width is going to be delta y. And the depth is always, the way I set these problems up, surface minus y. And since I called y equals 0 the bottom, and we filled it up to 3 feet, the surface level is 3. So it would just be 3 minus y. So force is the integral of 62.5. Length is 1. Width, delta y, becomes dy at the end. And then depth is 3 minus y. Then we have to decide on our limits. And remember, the limits refer to the strips, not to the water. So my strips are going from where to where? Well, my strips start at the bottom of the window, which is y equals 1, and go to the top of the window, which is y equals 2. So those are my limits. So we can pull the 62.5 out in front, and then just integrate 3 minus y. So I would get 3y minus 1/2 y squared. And this is going from 1 to 2. So when I plug in 2, I get 6 minus 1/2 times 4 is 2, minus what I get when I plug in 1, which is 3 minus 1/2. I'm just going to do that on my calculator, and I get 93.75. And put units on your answer. In the English system, force is measured in pounds. And then part B says, to what level can the tank be filled with water without exceeding the window's design limitation? Okay, well, we went up to 3 feet and it only had about 94 pounds of force, and it can withstand 312. So they can fill it a lot higher. What we're looking for then is, what is that depth we can fill it to? Where does that show up in the problem? The only place that shows up is in the expression for depth. If I call this h, like the height of water in the tank, h would be the surface level. Everything else stays the same. The strips are still 1 foot long or wide, however you want to think about it, and then delta y tall. The density of water doesn't change, so the only thing that changes is the depth. It would be h minus y now instead of 3 minus y. The strips in the window are still going from y equals 1 to y equals 2. So this was the answer for part A. And then for part B, the only thing that's changing is this. So again, you can bring the 62.5 out and then integrate h minus y with respect to y. H is a constant, we just don't know what it is. So the antiderivative would be hy, and then minus 1/2 y squared. This is going from 1 to 2. So I'd have 62.5 times 8. Remember, 2 is going in for y, not h. So we'd have h times 2, or 2h, minus 1/2 times 4 would be 2, minus what I get when I plug in 1, 4y. So I'd have h times 1, or h, minus 1/2. And then I'm going to distribute that negative. So this would be plus, minus, plus. Okay, combine like terms. So I have a 2h plus negative h, so that would be h. And then minus 2 plus 1/2. So that would be minus 1.5. So that's the force. And then they say it can withstand 312 pounds of force without cracking. So I just want to set that equal to 312 and solve for H. Okay, so I'm going to divide both sides by 62.5 and then add 1.5 to both sides, and that will be our H. And I get 6.492. And what are the units on that? Well, that was just a depth, so this is feet. So that's how much they can fill the tank. And it was a 7-foot tank, so they fill it relatively close to the top. I forgot. I thought that was the last part of fluid forces, but I do talk about some other scenarios here. Suppose that a rectangular tank with ends 4 meters by 6 meters is filled with water. Okay, pay attention here. They say the ends, not the bottom of the tank, the ends of the tank. So I'm just going to assume left and right. So the way I've drawn it, it looks like this part would be the 4 meters and this part would be the 6 meters. And then in the metric system, the density, the mass density of water is 1,000 kilograms per cubic meter. It says, is the hydrostatic force the same regardless of orientation? So it says the base is 4 meters versus the base is 6 meters. What I just drew is the base is 6 meters. So what if I drew it the other way and had the base be 4 meters and then like the height be 6 meters? So like this. So this part is 4 meters. This part is 6 meters. So they're both 4 by 6. The question is, will the hydrostatic force be the same on the ends regardless of how we arrange the 4 meters and the 6 meters? So we're only focusing on these walls of the tank. Now we're in the metric system. So force is equal to rho A D G. And the rho is 1,000. And the area we have to write as length times width. And length is going to be, in general, a function of y, maybe not in this problem, but in general it is. The width is delta y. The depth is surface minus y. I'll fill that in a minute. And then the g is 9.8. I'll just put g here for now. Okay, that's the same regardless. Think about a typical strip and the surface level in each case. Well, in this one, the surface level is going to be, I'm going to put y equals 0 at the bottom. So the surface level would be 6. In this other tank, the surface level would be 4. So I'm going to just separate into 2 different problems here. Rho is 1,000 for both of them. I'm not going to worry about units until the very end. And then the length, okay, I'll just do this one since it's visible. How long is a strip? It's 4 meters. I'm just going to put the 4. In this one, the length is 6 meters. The width is delta y for both of them. And then we need the depth. So for this tank right here, the depth is 6 minus y. For this tank right here, surface is 4, so the depth is 4 minus y. So the integral would be 1,000 times 6 times delta y becomes dy at the end, and then 4 minus y. I'll do limits in just a second. This one, it's 1,000 times length is 4, width is delta y, which becomes dy at the end, and the depth is 6 minus y. So let's look at our limits. And the limits are for the strips. So in this tank, the strips would be going from the bottom, which is y equals 0, all the way to the top, which is y equals 6. And the other one, The strips go from the bottom, which is y equals 0, to the top, which is y equals 4. So this one we can bring out 1,000 times 6. And I forgot my g. So times 9.8. Bring out all of the constants in both cases. I'm going to multiply the 1,000 and the 9.8 together, but not the 6. Okay, so I'll have 9,800 times 6, and then the antiderivative of 4 minus y will be 4y minus 1/2 y squared, going from 0 to 4. So I have 9,800 times 6. Okay, so I'd have, because I'm running out of space, I'm going to kind of do this in my head. Plugging in 4, I get 16 minus 1/2 times 16, which is 8. 16 minus 8 is 8, minus both times I plug in 0, I get 0. Okay, so I'm just going to leave it like that. This one, I'd have 9,800 times 4, and then we'll have 6y minus 1/2 y squared. So I get 9,800 times 4. Okay, so I'd have 36 minus 1/2 times 36, which is 18. 36 minus 18 is 18, and both times we plug in 0, we get 0. All right, so they both have 9,800. 6 times 8 is 48. 4 times 18 is bigger than that, right? It's 72. So it definitely matters which way we have the tank oriented, okay? So is it the same regardless of orientation? No. Okay, the next question is, what if the tank is only half full? Does that mean then the force is half of what it was when it's totally full? Well, let's see. Let's just do it for the first one. So if it's only half full, then a couple things change. My surface level is just y equals 2, and my strips are only going from 0 to 2. After that, there would be no fluid force on it. So when I set up the integral, the top limit changes to 2, and the surface level changed to 2. So again, I'm just going to bring out, the constants. And so I get 9,800 times 6, and then integrate. So 2y minus 1/2 y squared. This is going from 0 to 2. So when I plug in 2, I get 4 minus 1/2 times 4, which is 2. Both times I plug in 0, I get 0. So I end up with 9,800 times 6 times 2. So it's not half, right? It's a fourth for this one. Maybe it's different for the other one, but it's definitely not half of what it was. That was the question. Okay, I think that's it for the hydrostatic forces.